Hey guys, I'm Joey. My blog post is about a case study done by the American Journal of Biological and Environmental Statistics. The situation covers a real life implementation of a linear programming profit optimization problem on an Ethiopian chemical company in 2016. So the factory is located in Adama, a city 90 kilometers out of the capital, Addis Ababa. The plant's main revenues come from producing two different compound related products. Sulfuric acid is used as a medium of producing things like car batteries, and aluminum sulfate is used for things like purifying water for drinking. Both of these products must pass through three different stages in the manufacturing process: reaction, filtration, and evaporation. These will later turn into the machine hour constraints in the LP problem. And finally, as of 2016, the two products were sold at different price points and have different unit costs of production as well. Sulfuric acid is more costly to produce and also sells for a higher price at market, while aluminum sulfate is cheaper to produce and sell. In identifying the problem, the researchers collected data by speaking to various managers who determined how much to produce of both products. It became clear very quickly that everything was done by trial and error subjectively without using a consistent model. As a result, production was really inconsistent year over year, and so were the profits. So the team convinced management to use instead a maximum value linear function on a set of restraints, or an LP, to determine decision making. They did this by showing four main areas of concern that the company was dealing with that could be included or considered within this type of model. Due to imports from other countries, they could only sell at most 5,000 to 6,000 tons per year to consumers. Also, the factory was consistently producing only 20% of its designed capacity on average of the two products. And mentioned earlier, the three stages of production could be used as machine hour constraints. And then finally, with two different products that sell for different amounts and cost different amounts, this model could help determine the optimum mix to produce. So we've recognized that the type of problem here is in the product mix category. The research team also considered the four major linear assumptions that we talked about in class while turning the data into a model: proportionality, additivity, divisibility, and the certainty assumption. The objective function is to maximize profit, Z, based on the gross profit coefficient terms for products 1 and 2 and the two decision variables. There are also 6 constraints used. Constraints 1 to 3 are the machine hours that can be spent on each product in the 3 different stages. And constraints 4 to 5 are the demand constraints per day, which translate to about 6,000 tons per year. And last are the 2 non-negativity constraints for both variables. Running the solver in Excel with the simplex method, the optimal feasible solution was to produce 6,000 tons of aluminum sulfate, which was the maximum amount allowed, and then using the rest of production for sulfuric acid, which leaves a small amount of demand unutilized. This leads to a maximum daily profit of 107,000 BER, or over 32 million yearly.